Yes. So let other people join, and then we'll start at 6, I guess, 5 minutes past 6, maybe. So let's just a second. Am I visible or not? Maybe this way. So, welcome everyone to today's session. This is session number 2 of this course titled as Sensors and Actuators. This is a problem solving session and this is conducted by me, Shomnath Bhattacharya. I am a PhD student in IIT Jodhpur and so this is a brief details about me. So, currently I'm pursuing my PhD in Department of Electrical Engineering, IIT Jodhpur, and my research domains are like my research interests are towards flexible and organic transistors for neuromorphic computing applications. Previously, I have completed my bachelor's in physics and master's in electronics. And we are conducting the class every Sunday from 6 to 8 p.m. And so this is the second class. So this is the basic course layout. I have already discussed it in the previous class. So in this class, um, in the previous class, what we have done is that we have known about the basics of energy transformation. So sensors, actuators, transducers, and what kind of a transducer, sensors, and based on different principles, how many types of sensors are there, what is the basic thinking that if you are using your transducer sensor or something like that for a specific purpose, what kind of a design objectives you need to have, what kind of a material you need to use, and what kind of a fabrication procedure you need to follow. Everything needs to be optimized for your use case only. So what is best for my use case is not may not be useful for your case as well. So for different work and everything, we need to find a optimum device that works for specifically for our need and everything. So previously we have learned about the transducer, sensors, and actuators. So what are sensors, what are actuators, and what are transducers? Now we need to know more in depth to these things. So how these devices are fabricated. So how a actuator or a sensor is fabricated, what are the techniques involved. So like there are multiple techniques. So previously we have known a very basic about MEMS, that is micro electromechanical systems. So in that there was NEMS as well. So as in this course we are mostly focusing towards MEMS because like we are only talking about the micro domain. But apart from that, everything in the NIMS will also have a similar kind of a techniques used, similar kind of a protocols maintained and everything. So the main aim of this lecture is to know more basics about the sensors and actuators, how they are fabricated, so what kind of a techniques are used to fabricate them, what kind of an environment is required to fabricate them. So there can be dust particles or something like that, and because of that, your device may stop working after a few runs. Let's say after 2, 3, 4 runs, your device may stop working and everything. So you need a complete device that works for a long time and that also works reliably as well. So it should work for a longer time, but it also should be reliable over time as well. And with continuous use and everything, it should also retain its functionality and everything. So in this lecture we'll know what are the clean room protocols? How clean room? What is clean room? First, we need to know that. Then, what are the protocols maintained there? What are the procedures to enter a clean room and everything? And then we'll learn more about the techniques involved in this process and what kind of equipments we are using inside this clean room and everything. So so this is also a basic thing. So this is our second thing. The main thing we'll learn in this one is introduction to MEMS. So in the lectures, I guess you all have learned about the basics of MEMS and everything. Then the second part is microfabrication and deposition techniques. So there are several deposition techniques, physical and chemical involved and those things. Then further, we'll know more about the clean room protocols and procedures in which environment these kind of sensors are being fabricated and all. So the first topic in this lecture is MEMS. So what are MEMS? MEMS are micro electromechanical systems. So these are majorly divided into four different parts. The first part is microelectronics. So mainly this is the processing part. You can say this is the processor, or you can also say this is a brain. So what it does is that it takes the input and then it processes it, and based on that it gives instruction to the actuator part. Then the next part is the next. Oh, let me write it like this. Then the next part is microsensors. So what are microsensors? These are basic sensors that are in micro, micro in like micron sizes and everything. So in the micrometer range or something you can say. So the main aim of these things are gathering data, gathering data, storing, and transmitting to the brain. So what it does is that it gathers data from the environment or the nearby location and everything, and based on that, it stores some of the data and very few, obviously, and also it transmits the data to the brain. So what brain processes the data, and based on that, it gives inputs to the or it gives outputs to the actuators. So the next part is micro actuators, micro actuators. Now, what does these do? So this is also similar, right? So sensors gathers the data, microelectronics processes the data, and then micro actuators, what it does is like it triggers to activate an external or peripheral device. So what it does is that it triggers to activate external peripheral device. So so the mainly from a computer perspective, you can say like so any mouse or keyboard or something you give input to the computer. So that is kind of a microsensor. Then the CPU it processes everything, the data and everything, and then it gives output to your screen. So that is the micro actuator part, and your CPU is nothing but the microelectronics part. Now, these three are the main or the key parts of this MEM system. But another part is microstructures. So, what are microstructures? These are very small structures that that is directly built on different substrates and everything, and uh, like it provides the necessary base to all three. So what it does is that it is the most foundational part of this MEM system, and based on these microstructures, it provides necessary functionality to microelectronics, microsensors, and microactuators as well. So MEMS is kind of a made of these four different parts and everything, and then in the lectures I guess you all have seen more detailed instructions and like what have been like going on and everything. So now we'll move on to the next part, that is the microfabrication. So we need to have more time in that domain. Now, what is microfabrication? So that is completely fabrication, right? So like you are just trying to make a device or trying to what do we say, like trying to realize an idea through an electronic device. So it can be a sensor, it can be transistors. Like if you want to, let's say, like what does a transistor do, like amplify. So if you want to amplify some signal, or even if you are trying to reduce the noise or something, so you need a filter or something, you need to fabrication, you need to go to an fabrication lab, and based on that, as it is in a micro domain, so let's say it is the microfabrication. So now microfabrication, three of the most important things are: first one is obviously a clean room environment. We need to maintain a very clean environment. Why is it like that? So in if you are making a very large device or something like that, right? So you don't need to like ensure that let's say a cricket ball or something, it directly falls onto the device or something, right? So in that case it will disrupt the device's behavior and disrupt the device's working and everything. But in case of a micro device, so it's already in a micro dimension and everything. So even a very small like dust particle or something, let's say you have a channel, let's say a microfluidic channel or something. So if you have a this channel dimensions are 1 micron. Okay. Now if let's say you have a um, let's say you have a particle, if you have dust particles of 500 nanometers. So what happens is that if there are, like, let's say, two particles, so what will happen in this case? Or let's say even let's say if you have a single particle as well. So based on that, what will happen is that the flow of the fluid will be disrupted. In some cases, like, a high pressure will be created here. And similarly, if there are, let's say, two more bigger particles, let's say 600 or something like that, or 500, that is like situated back to back, like this. So like this and like this. So in this case, what will happen? It will completely stop the flow as well. So because of that, any kind of a small dust particle or small debris or something like that, that will disrupt the total working of the device itself. So we need a very clean environment that is free from dust and everything. So there are several different kinds of a clean room, and we'll discuss that later. But the main idea is that we need a very clean environment that doesn't involve any kind of a dust, that doesn't involve any kind of a free usage of your hand, or let's say like dandruff particles, or like dry hair or something like that. So broken hair just like gets falls onto that your device or something like that. So you need to ensure that you are not contaminating the device itself, and also the environment is not contaminating the device itself. So this is the basic thing, the basic understanding of a clean room environment. Why is it needed to fabricate a device in a clean room environment? Now the next portion is the deposition techniques. So based on different materials used, based on different techniques used, and these things, we need several different kinds of a deposition technique and pattern techniques. So there are several different pattern techniques and deposition techniques, and we need to choose it wisely because some may cost you more for each run, some different some may use or waste materials more. So let's say if you are depositing a gold, so if you are using a technique that you like that, what do I say? Like, so, like, if you are using a technique that uses a lot of gold, that is a waste of money, right? So if you are preparing a single device or two device, you need to have a complete goal that I need to optimize the device so that I can lower the cost. So I need less gold. I need a proper technique that provides a complete and very thin film of gold and everything based on your need and everything. So there are several different kinds of deposition techniques and everything. And the final one is the patterning techniques. So not always you will need a very clean thin film of a gold or a metal, or let's say a polymer or something. You need patterned electrodes, patterned devices and everything. Why is it needed? So let's say, so in most of the cases, so if you are in some of the systems, so let's say if you are just wanna deposit something, you just evaporate it or sputter it or something like that, and based on that there will be an uniform deposition of that material. But based on pattern techniques, what will happen is, like, if you are, let's say, if you are like patterning it, you can make it like this. So let's say you want a stripe pattern or some kind. You can make the pattern like this, and the deposition will be like this. So based on your needs, based on your design, based on your patterns and everything, you will have to choose your deposition techniques. Based on your need, you will have to choose the patterning techniques, and also in every each other cases, you need to consider the cost of everything. So if your patterning technique is costing you more, but you don't need that much like fine tuning of each pattern or something, you can use a very lower cost patterning technique as well. So now let's move on to specific deposition techniques. So there are several deposition techniques as well. So mostly they are divided into two major parts. That is the physical deposition technique and chemical deposition techniques. So majorly the physical one is known as physical vapor deposition, or PVD, and this chemical deposition technique is known as the chemical vapor deposition, or CVD. So there are different kinds of PVD techniques and there are different kinds of CVD techniques as well. So let me just use a different color, maybe something like a blue. Yeah. So there are several physical vapor deposition techniques. So in physical vapor deposition, what happens is that a vapor is physically deposited onto another substrate. So the main thing is that, so if this is your target means that where you want to deposit the film, and if this is your source. So if you want to deposit this source material onto the target directly, you will need a physical vapor deposition technique. Just a second. So just a second. Just give a moment. Hmm, hmm. Yeah. So if you want to directly deposit a source material onto a target material, you will need a physical vapor deposition technique. So it will directly be transferred or directly be deposited onto that target material. Now, if you want to deposit a material through chemical reactions and everything, so this is through direct way. And in this case, what happens is that if you have a target, let's say, and what happens is that here chemical reactions happens, and the source material gets deposited onto the target material itself. Now, so there are several different kinds of PVD techniques and CVD techniques, and the most common ones are obviously evaporation, and another one is sputtering. So we'll know more details about these deposition techniques later. So I'm not going into that much detail or something, but let's say that evaporation creates a very low cost film and sputtering creates a more uniform but a higher cost film. Now, evaporation can be of different types. So, evaporation can be like based on heat. So, it is known as the thermal evaporation technique, and another one is E-beam deposition technique. So there are two different evaporation techniques, majorly two different. So there are thermal evaporation and E-beam deposition. So thermal evaporation is suitable in case where there is a boat. Another thing I have to first discuss. Yeah. So in thermal evaporation, what happens is that your substrate or the sample is put on the top side of the chamber, and in the bottom side there is a resistive boat. So this boat is heated through resistance and with a very high flow of electrical current. Now this is your boat, and this has a very high melting point. And if you are putting your material onto here, so if you are heating both of them, this one will not evaporate or get vaporized, but this one will. And what will happen is like this will create a flow of this gas flow of this material, and everything is like under plasma environment. So what happens is that with a very high vacuum, that is 10 to the minus 6 torr vacuums, so what will happen is that there will be a deposition of a thin layer of this material onto this, and this process is like normally known as a thermal evaporation technique, and we'll learn more about this later. And in e-beam, what happens is, what the problem is that in e-beam, if the material that this one, if the melting point of this is much higher than the boat itself, so you can't heat that, right? So if you are heating the boat, then the boat will melt first before the material itself. So in those cases, because let's say in silicon dioxide, what happens is that silicon dioxide has a huge melting point, and any kind of a boat will not sustain that kind of a heat. So what we need to do is that we will need to use a specific kind of a system. So here what happens in e-beam is there is a crucible. So in this case there is a boat, but in this case, there is a crucible, and E-beam directly hits onto the sample or material, and it gets evaporated directly onto the sample itself. So this one is this, and sorry, let me erase it now. So inside a crucible, what happens is that the process is very similar. It creates a flow. The flow is towards this way, and there's a deposition of this material onto this. So both techniques are similar, but for a basic thing, that if your material's melting point is much higher than the boat's melting point, you will need to use e-beam, and that is much costlier as well than the normal thermal evaporation technique. Now in sputting, what happens is that, so let's brief that a little as well. So inside an inert atmosphere, what happens is that you are sputtering a material directly onto your sample, and particles flew out of it and get stuck onto this and creates a very uniform thin film, but it does involve more cost as well. So these are the most common PVD techniques. They, in these cases, what happens is that you are depositing a thin film or a layer through a physical process. So either you are directly involving ions that are directly connecting onto the sample itself, otherwise you are just evaporating or creating a vapor, and the vapor is directly getting stuck onto the sample itself. So everything is a physical process. Now, in this case, what happens is that in case of chemical vapor deposition techniques, one of the most common one are LPCVD, AMOCVD, PECVD. So these are based on different conditions used. So LPCVD is a low pressure one, and based on this, under a plasma environment and different environments, everything works. One of the most new and unique one is the ALD process. So what is an ALD process? In ALD, what happens is that you have your sample here. This is also, everything is like happening inside a chamber itself. But let's say if you are putting this, so what happens is that in the first case, let me take a different color maybe. Yeah. So in the first case, what happens is like you have two different kinds of a molecules. So you have like these kind of a molecule, and these molecules get stuck onto it. No, let me change the this thing. So let's say you have a molecule something like this. Now this molecule will create a chemical reaction with this top surface of this sample. So what will happen is that it will create something like this, and multiple molecules will be stuck onto this. Now if we are just changing this, so we are just removing this, now we are giving an let's say an intermediate molecule like water or something like that, water vapor or nitrogen vapor or something like that. What will happen is that with the purge of that water or something, what will happen, these molecules will be changed. Sorry, just a second. This molecule will be changed with this. new molecules that may be water or something like that. Okay, so the molecules have been replaced with water molecules. Now, if we are giving the next purge of the first or initial molecule, what will happen is that even let's say again we are giving this molecule. What will happen is that this thing will be removed. Now there will be another chemical reaction, and this will look like this, and everything will be interconnected. So this will work like this. So this thing, both will be connected, and these things will be there. So you can see in this case, you can next again, if you are trying to, let's say, purging a water purge and everything, then the top atoms will be converted into the H2O atom. Then again, if you are purging this same material, there will be chemical reactions based on different layers, and you will create layer by layer deposition of that material. Now the main problem with this thing is that, let's say, the main advantage of this thing, so the main advantage of this technique is that it gives a highly pure and uniform film. So it gives the most pure and uniform film. It is highly costly, but in several cases, like there are different kinds of ALDs as well. So there can be a thermal ALD, there can be a E-beam ALD, and there are several things. But let's remove those things. But in this case, what happens in thermal ALD, you are giving heat to the sample itself, because then the reaction will happen at this point. Otherwise, it won't happen. So you have to give like temperature to the sample itself. Now, the main problem with this thing is this is very slow. What is the main disadvantage? It is very slow. So for a deposition of, let's say, 40 nanometer, in my case, let's say in my research and everything, I have used ALD. So in those cases, it took about 12 and a half hours to only deposit only 40 nanometer. So that is really very thin layer. So for 40 nanometer, it takes about nearly 13. And even if you are trying to deposit something, you need to clean first, and then you need to first, like if the instrument hasn't been run for, let's say, a week or so, you need to clean it first. So that will also involve at least 3 4 hours. So in a nutshell, you will at least need to use the whole day, that is 16 to 17 hours, to deposit a single material of only just 40 nanometers. Or even if you are trying to deposit a very like thin one, that is, let's say, 5 or 10, that will also take you 7 8 hours. Now the problem is there, but it is very highly pure and also uniform as well. So this is the main thing in this case, and I'm talking this about ALD. So these are different deposition techniques. So we'll learn more about these in detail and everything in the subsequent lectures and everything. So now let's move on to different patterning and etching techniques. So why do we need this patterning and etching, right? So first we have deposit the material, and if we need to have a fine patterns, let's say, so through different deposition techniques, let's say we have a square like this, and we can deposit in whole of the material itself. But we need a specific pattern. Let's say we need the device to look like this, look something like this, and this can be the whole one. And we need only the material here. So there are very cheap processes as well, and there are much like costlier processes as well. So one of the most important one is photolithography, and one of the most used cheap one is shadow mask usage. So let me first briefly introduce you to this shadow mask usage. So what happens is that if you are directly evaporating some material onto your substrate, you can have a shadow mask. So what is a shadow mask? Shadow mask is like this. let's say you have a metal mask and it has the pattern inside it, right? And what will happen is that apart from the like apart from these holes, everything will be blocked. Every other metal particle and everything will be blocked here, and based on that you will get the pattern on the sample itself. Now but there's a problem with this kind of a technique. So there's the issue of shadow itself. So if you are trying to make, let's say, a square of 100 cross 100 nanometers or micrometers, let's say, you will have several problems with that. And if you are going to a fine detailed pattern and everything, you can't use these kind of a techniques. But if your devices are big or your requirement is not towards that kind of a thing, you can use this. Now let's move on to the next one. That is the most important one, that is called a photolithography. So what happens in a photolithography is that, so in case of photolithography, there are several different chemicals involved as well, and there are several masks involved as well. So let me talk about the masks as well. So there are like different patterning masks. So these are called the bright field mask and dark field mask. So what is a bright field mask? Bright field mask is a mask. Just a second. No, let me talk about the PR first. So there are two different kind of masks. There is a bright field mask and there is a dark field mask. So there are several different kind of a masks there. Now there are the chemical that involves the like that involves the printing of these kind of a pattern onto something. And so the chemical is called PR or photoresist. So these photoresist can be of two types. So what are the two types? The first one is known as the positive photoresist and there are the negative photoresist. Now, what happens in these cases? So, based on your choice of photoresist and mask, you will involve different kind of a patterning techniques, and you can also utilize them, let's say, in different procedures and optimizing your devices as well. Now, what happens in this case is that, so I'll like explain the photolithography and everything in subsequent lectures as well. So I'm not going into total details of photolithography, but the basic idea behind photolithography is that if you have a substrate, let's say a silicon substrate like this, so this is completely silicon. Now you are depositing a metal through any kind of a deposition. Let's say you are using thermal evaporation. So this is the metal layer. Now you want a specific pattern onto this. So what will happen is that you will deposit a layer of PR onto this. So this is PR. Let me write it down. This is PR. This is the metal and this is your substrate. Now, what is the easier thing to do is that if you are going to pattern your PR first. So if you are patterning your PR, what will happen is like this will look like this. So your substrate will be here first, your metal will be like this, and then your PR will look something like this. Okay. Now based on this, you will expose UV light onto this material, and from that you can see after removing your PR and everything and the last step, your substrate will look like this, but your metal will also follow the trend of the PR that was earlier exposed and everything. So it will look like this. So your intended pattern will be printed onto this. So this is the basic thing of photolithography and etching, and everything is involved here. So what is etching? In etching, what happens is that you are etching away the material that is not like not needed or not necessary in your case. So there can be two different kind of etchings as well. Let me talk about etching first, and then I'll move on to photolithography and everything. So there can be two types of etching. There can be a dry etching technique. So in dry etching, what happens is that you are like, um, let me talk about this first, but let's fine. So there are two types of etching: dry etching and wet etching. So in wet etching, what happens is that it uses some chemical solutions and everything. You need to dip your solution into it, and based on that, whichever part is not your intended part, it will dissolve away, or it may stay as well. So based on your choice of photoresist and choice of different kind of lights like UV lights and everything, so it may dissolve away, or it may stay there stronger, more stronger, right? So based on that, it involves in basic thing is that it involves a use of chemical solution in which you dip your sample or something, and based on that. But in case of dry aging, what happens is that several different substrates, several different metals are like can't sustain the use of several these kind of agents. So the solution we are talking about this chemical is known as agents. So these agents are very toxic and everything in nature. So because of that, several different materials and several different polymers on those things can't sustain these agents, and that's why we need several different techniques known as the dry aging techniques. What happens in this case is that different kind of materials are either sputtered or directly dissolved with gas or plasma. So this, as it doesn't involve any kind of a liquid or those kind of a things, that's why it is called as dry etching. So these are the basics of etching techniques. There can be dry etching, wet etching. So based on your need, you will have to choose one and utilize that inside your device fabrication. Now, I was here in the photolithography section. So there can be two types of masks, as I was saying. So we need a glass mask. So that is the basic thing we need to know. Now, what happens in a bright field mask is like this. So if you have a mask like this and your pattern is, let's say, like this, okay. So in this case, if your pattern is like this, let's say, so based on your mask, so if your pattern is like this, so this one is a darker portion that is made out of quartz and these things, and this one is the lighter portion that is made out of glass and everything. So let me write it down, quartz or something. This one is a glass and something. So if the most part of this mask is the pattern is made out of quartz and these things, and the most part of the one is brighter, so it will be known as a bright field mask. Similarly, if you have a mask in which the pattern is like this, but everything entirely is made out of quartz, so the pattern is same. Ignore my poor drawing skills and everything. So if the pattern looks like this kind of a thing, everything looks dark, so this is a dark field mask. Now based on the choice of your photoresist, you will have either a negative pattern or a positive pattern. So what is a negative and a positive pattern? So if you are using a positive photoresist with a bright field mask, so let's say we are using a bright field mask, so like this, and we have a very simple pattern like this, square or something like that. So this is a bright field mask. And now if we are using a positive photoresist, so this PR layer is positive or negative, right? So if this PR layer is positive, what will happen is that we'll have a directly similar pattern onto the sample itself. Now if we are trying to use a negative one, so both are coming directly from this. If we are using this one is a positive one, this is a negative one. Now, if we are using a negative photoresist, what will happen is that the pattern will look something like this. So in case of, let's say, in older cameras and everything, you would have a negative or a reel or something kind of that, and based on your printing techniques and everything, what would have happened is that the darker portions will get the more light and the lighted portions will get more dark, and that is the concept of negative or negative films in photogenic cameras and everything. So in this case as well, the negative one gives an opposite pattern of the mask itself, and in case of positive it gives an exact replica of your mask onto the substrate. Now then another question arises, right? So if we are using, let's say, a bright field mask with and positive photoresist, so it's giving the exact replica of your image itself. Now what will happen if we use an dark field mask with a negative photoresist? Both will give the same structure, right? So any one of you can try to answer this. The main concept is that if we are using a bright field mask with a positive photoresist, it should give the same same replica of that pattern that is onto the mask itself, and it will be transferred onto the substrate itself. Now if we are using a dark field mask with a negative photoresist, it will also be there. So what is there any difference, or which one should we use then? Any idea?
Is it because it depends on the substrate?
No, the substrate is same in both the cases. We are just using the bright field with the positive one, dark field with the negative one. And ideally, we should have the same pattern, right?
Right. Ideally, it should be there.
Yeah. But what do you think? What can be the problem that we won't use both these options? There will be an ideal option that will use in most of the cases. And what is that?
Is it the dark one, the dark photoresist?
No, the bright field one. Yeah, so the left one is the most suitable one. And why is that? So, do you know
Uh,
which one is the most costlier one? So, everything comes out of this cost thing and everything. So, which one is costlier, quartz
oh,
or glass?
the dark one would be more costly because I think the for manufacturing it we would have to tint it or something like that.
Yeah, so like the point is like which one is most costlier, glass or quartz? Obviously, quartz, right?
Glass would be costlier than quartz, right?
No, glass means normal glass. You have a quartz. You have to pattern the quartz inside the glass as well. So you have to consider that as well.
Oh,
And you will have
okay,
to
okay, okay. So,
have a very high quality quartz that will that will block the UV light and everything. So everything is like pure one, not a basic glass or not a basic quartz as well.
okay,
And also the cost of this positive and negative photoresist comes into account as well. So
okay,
mostly what happens is that mostly everybody uses this bright field mask, and because of that, everybody uses the positive photoresist. And there are issues of this environmental stability of this photoresist and everything. So in most of the cases, like in all the labs, so people generally, yeah, I'll share it. Yeah. I guess everyone have the previous link of the previous one. So the week 1 lecture PDF I've already shared there, and it will be uploaded there by today itself. So this is the basic thing that these two things are ideally equal, And even if you are trying to like do everything and like everything in an ideal way and everything, both of these should give you an exact same replica of the same pattern. But there are several things like comes into mind that you need to understand the cost. You need to understand which one is easier to etch away as well. So if you are etching very small portion of something, it is much easier. And if you are etching away the like let's say 90% of your pattern, that will be also hard as well, right? So that also needs to be like taken into account. And there are several things as well. So in these cases, there are very like there like you waste at least 90 to 80% of your material itself. So that also comes into account as well. So now let's move on to the environment itself. So further, I'll discuss in the next classes. So I'll discuss the deposition techniques, each one, and I'll also explain this patterning and everything with images and everything. Here I am just as I am giving the basics and everything, I'm trying to draw it here now, but afterwards I'll use like photos from the internet itself or from our lab itself. Okay. Now, so first thing we are going in depth is that the clean room. So as we know that I have already discussed that there are three major things. The first one is the clean room environment, that is the environment we are fabricating the devices in. Second is deposition techniques, and third is patterning techniques. So the most important one is your clean room. And in clean room, sorry, just a second. Yeah, I guess. Yeah. So, so what is in clean room, right? So you need to eliminate any kind of a dust particles from your devices and everything. So you need to protect your device from these dust particles. So there are several different kinds of clean rooms here. So I guess I if I can zoom in, yeah. So based on different ISO standards and everything, so there are several different kinds of clean room. So there are this one, the ISO one, or which doesn't have a class as well. So in most of the cases, we still nowadays we still use this class system. So either class 1, class 10, class 100, class 1000. These are the most common ones, and there are room air as well. So open air open air rooms are there as well. Yeah, you can say.
I have one question regarding this.
Yeah.
Like when we are describing the clean rooms, what exactly are we scaling it on? Like the number of particles present there.
Yeah, so
Like what?
inside a cubic meter, so you can see it here, right? Inside a cubic meter, what is the maximum number of particles permitted? So let's say you can have 500 particles. If you have less than 500 particles, you can classify it into a clean room. And also the radius of the particle is also taken into account as well. So this is the particle size one. Let me just change the ink as well. So based on this, you have different sized particles as well, and also the number of particles both comes into account.
So if I say that it is a class one, then it would be ISO 3. Like is it like that?
Yes, yes, it's exactly like that.
Oh,
So
okay.
now the point is that if like let's say if you are going to TSMC or something like that, you need if you are working for space applications and everything, you will need to ensure that there are no dust, and the clean room standard needs to be at peak. So these are called the ISO 1, ISO 2, but in most of the cases in India itself, so the clean rooms are like class 1, class 10, class 100, class 1000. These are the most common ones, and there are also in several like several institutes and everything, even people fabricate in clean room like in the basic room air, or let's say you are maintaining a clean environment, that's it. So there are also labs and everything like that. So now the thing is that as we are fabricating the device in an R&D environment, we are testing, we are trying to optimize the device and everything. So we are not ensuring the long-term capability of these devices, and we are not also checking the long-term usage of these devices. So that's why we can also fabricate it in a room air. But it's best to have a facility like in those people who have this like thousand, at least 10,000 you need. So the main thing of this 10,000 is that you can maximum have 2930 particles of this much radius. So like 5 micron sized particles, you can have up to 2930. If it's over that, it falls under class 100,000. That's a major point. Now, the complexity arises here is that you don't have a particle of only 5 micron, right? You can have a complex thing like you can have a particle with zero point 0.5 micron, 1 micron, 5 micron together. And you have to then calculate that. But this is a basic standard rule or something like that. Yes, if you have any question,
Okay.
you can ask. Yeah,
No, no, I got this now. Thank you.
yeah, yeah. So this is the basic standard or clean rooms, and here you can see our clean room in IIT Jodhpur. So like I work under this thing. So this is the lab one, that is the fabrication lab one, and this is known as the AIoT facility there. And this is the horizontal three stack oxidation furnace system and everything. And everyone is wearing a gown and everything. And you can see here, this is not an entirely clean room, right? So this is not a very highly graded clean room and everything, but everything is kept clean. That's the point here. Everyone is wearing a gown, everyone is wearing a gloves, nitrile gloves and everything. Everyone is wearing a cap and these things. And in here there's also another problem as well. So this guy has a beard. In most of the cases in international labs and those things, they don't encourage you to have beard or something like that, because then hair particles or beard particles can fall onto your device and everything. And even if you have that, you have to properly cover it. So you have to wear a complete face mask and everything. So in most of the cases, what we do in our lab or something is we use a basic face mask and we try to cover our faces and everything. And so like basic cuff or something like that. So even if you are just just coughing or normal like that, and you don't have a fever or you don't have a cold or something like that, so based on that, the flow of air and everything will contaminate your device and everything. So you have to completely cover everything. And this is our chemical benches. So in there as well, we use nitrile gloves and these things. So this is the basic thing of a clean room. But now we need to understand how to enter inside a clean room and what are the protocols being followed and why do we need to follow everything in a series of way. So even if we are trying to let's say doing something in a wrong order of way, there will be problems. So let's say, so here I guess you guys can see it. So the basic thing is that the first one is the buffer cap or the hair cap, and then it ensures that no hair particles or something falls off. Let me I don't think let me just write it down here in a very small way or something like that. So so the first thing what we do inside our lab is that first we work onto a mat that is called a tacky mat. And onto the tacky mat we try to at least remove the particles from our shoes. This is not the do's and don'ts. Okay, first we try to remove all the particles attached to our shoes and everything. Then after that what do we do is that we remove the shoes itself. And there are shoe racks and everything, so we need to put we need to arrange the shoes and those things. So now after that what we do is that we wear lab slippers. So first we need to wear the lab slippers that also stays near the shoe rack and everything. So you are just removing your shoe rack and removing your shoes after cleaning them. You're just putting it onto a shoe rack, and just beside that, so there's a entire separate compartment, and you need to take out the lab slippers and you need to wear them. Then after that, what happens is that you need to so after that you enter enter inside and changing room, some kind of a changing room, or let's say there was an I don't exactly remember the name, but the room also has a specific term. So you enter inside that room, and after that changing room, what you first do is you just wear this cap, or you can say the head cap. First, you need to cover your hairs, so no kind of a hair particle or something falls off. So you need to cover your hair. So you need to wear this cap. Or sometimes if you have, so for ladies and everything, so for them the problem is that they have a long hair sometimes, and you have to like cover that. So there are hoods as well, different kind of hoods and those things. So they completely cover those like dangling hairs and those things. Then after that, what happens is that we wear a face mask. So these like face masks. So like in several cases that, as I was saying, like beards are not permitted inside and clean room in like international environment and those things. So in those cases, you are not allowed to like enter inside and clean room with a beard and face full of beard or something. So in India, I don't know about others like institutes, but in IIT Jodhpur, what happens is that we use a specific like a larger mask to cover our full face, and we use this kind of face mask. So after that, we put on this face mask, and after that, we put on the lab coat. Or in some institutes, they also have jumpsuits as well, and also like there are bunny suits as well. So like different kind of suits are there. In our case, we use this lab coat, and I guess in case of ISC Bangalore, there is also lab coat systems and those things. So like the shoot is like we just wear onto the shoot. Then what happens is that in case of wearing this shoot, there are also like instructions as well. So we need to put our feet first inside the shoot, and then we have to like, and the final one is that like I guess here you can see this process. So the first you need to put on this uh, put on uh, put on the shoot from from the bottom side of your body, and then finally you will put your arms inside it. And then the thing comes is that you need to wear any kind of a protective eyewear. So based on your use case, so if you need protection from let's say light or UV or a very high intensity light like used in lithography, like deep UV lithography, so there are several kinds of lithography and everything. So you need to wear these kind of protective gear. And otherwise if you are using volatile organic compounds like acetone and these things, you will need a protective eyeglass as well. So there are several different kinds of eyewear. So based on your work, you need to wear that. And after this eyewear, you need to, if you are going inside the most what do I say, like the most so there are several sections of these like clean rooms. So in our clean room, there is a separate section where you are just completely fabricating the devices and everything. So you don't need to wear a different kind of shoes. But if you are going inside a chamber to perform some characterization or something, you need a change shoes. So these shoes are I don't know what they are called, but these are different kind of shoes. These kind of look like boots, and they like cover your the base part of your bunny suit as well. So these kind of a shoes are also wear. And after that, all the protective equipments and those things. So like tweezers from let's say we have to collect our tools or equipments. Let's say, so this includes like different kind of tweezers in my case. Sorry, just a second. Different kind of a tweezers, and I also use different kind of a materials as well. And we have to collect those materials. Everything is kept inside this clean room itself. And there can be use of several kind of agents like acids and these things. So you also have to collect them at this moment and everything. So and also like lab necessary equipments like what do I say, like lab stationaries as well. So you are not allowed to take your copy or book or something like pen, pencil or something like that. You can't take it inside the lab itself. So there are separate lab supplies there, and you have to take those lab supplies and like from the book and these things. And also you need to know that like no kind of a pencil or these kind of a things you can't take it inside, and even you don't have it inside your lab as well. So you need to use some kind of pen, ball pens in most of the cases. and so you have to use those things inside the lab, and then you can there's also a separate rack to keep your bag and your belongings outside the lab itself. And you can't bring your own like stationery, even if you are taking a tool inside, it also involves a very like lengthy process as well. So if you had to give it to your technician, he will clean it, then it will go through and a proper cleaning process and with some airflow and those things. So it takes time, and based on these things, so you also at this time, so it is not 12, but you also need to take several kind of a different gloves and these things. So there are nitrile gloves, there are acid protective gloves. So if you are working with HNs and these things, you need, and like let's say HF is a very what do I say, like a very very it has a very high like risk of burning your skin and everything. It also burns through any kind of nitrile gloves as well, so you need a very like thick rubber gloves and those things. So these are called the acid protective gloves, and you need to use those. In most of the cases, if you are fabricating some devices or if you are characterizing devices, you need to stay away from several volatile materials as well, and also from hurting the device, like contaminating the device itself. So you need nitrile gloves. In most of the cases, I use nitrile gloves. These are all for dust avoidance. So let me write it down as well. So to avoid some kind of a dust. And so after these things, you are able to completely enter into the clean room itself. Now in clean room there are several do's and don'ts. I am not writing those down. So the main thing is that you need to walk slowly, very slowly. You can't like run or something. So even if something like, let's say, even if your material inside is inside an oven and you need to just go there fast, otherwise your material will get like destroyed or something like that. But you can't run inside a clean room, because it will disrupt the airflow inside the clean room, and that will disrupt everyone's work inside the clean room itself. And then you can't bring your own supplies. So even if you are trying to bring, let's say today you need a specific different kind of a tweezer, but you can't bring it today. So you have to give it to the lab technician. They will put it inside your lab supply section, and you can take it from there, or you can ask the authorities and they will provide that inside the lab itself. Similarly, after let's say using a workbench or something like that, like chemical workbench and these things, so you need to wipe it down very clearly, because the next person will have to use that bench after your use or something like that. And you need to like, what I generally do after my usage is that before using that bench, I generally clean it with water and these kind of things, and then after my usage I also try to clean it, and then it will be like readily usable for the next person as well. So these are the basic flow that you need to so these are basic protocols that you need to follow inside a clean room, and there are several do's and don'ts. You don't need to do that inside a clean room and everything. So with the class so if it's a higher class one, it will have more strict rules and everything you need to follow. And with a very lower class one, so like we also have several room air clean rooms as well. So like that is a space, that is a complete lab room that is just clean. That's it. Nothing apart from that. So these kind of a things, these kind of a rooms have a different rule sets, and different like class like 1,000 or class 10,000 rooms have a different kind of a different kind of a rules and those things. So this was it. And if anyone have any question, you can ask me right now. Otherwise, I'll move on to the questions and these things. Anyone have any question? Anything regarding to what I have already spoken about. So from the basics of microfabrication towards deposition techniques, the basics of deposition techniques, patterning techniques, and then the clean room basics and what are the clean room protocols and these things. If anyone have any questions, you can ask me.
One have that
Yeah, yeah, sure.
bright, the bright one and the dark, that lithography in the lithography section which we were discussing.
Hmm.
So that there was bright mask and a dark mask, right? So
Yeah.
what was the answer to it? Like which one is cheaper and which is most used and why is it?
So in most of the cases, people tend to use the positive photoresist, and because of that, the bright field with the positive one is the most used one. But ideally, both should give the same and exact same replica of the intended pattern and everything.
So why is it that this one is used preferred over the other one?
Yeah. So in case of if I can show you it, let me just if I can show you. I'm not sure if you guys can see it. I'm not sure. No, no, no. Just a second. I have to search it from here. Just a second. Yeah. So if I can show you, I guess you guys can see it, right? So if you are just searching a positive photoresist cost or something like that. So if you are searching, you can see it that roll is a very small one. So we generally tend to buy a bigger one that is known as barrels of these materials, and the distributors, what they do is that they purchase these barrels and then they divide these barrels into smaller bottles of 1 liter and 2 liters and 10 liters and these things, and then they supply it. So you can see the basic photoresist. So like I'm not going into the specific details of which kind of photoresist and everything, but you can see it is around 2500 and everything, right? In nearby 2500. And if you are just checking this, I'm not sure what will be the result, but let's see. Generally, these are most costlier ones. Yeah. So here they are cheaper. I'm not sure why. Okay, okay. It is searching SU8. No, not the SU8 one. If we are going to, let's say, SU8 is the most used one. So if we are going inside, um, let's say, bright mask was, I guess it's visible, right? Yeah. No, I don't think you guys will get to know from this. But in case of bright field mask, the the pattern is very small, and based on that, the like the bright field mask. So if you are going into like generalized masks and everything, bright field mask will cost more. But if you are going into like several smaller patterns and these things, bright field mask will cost you less. But in case of like dark field one, it will cost you more if you are going into several like smaller fine-tuned details and these things. So based on the cost factors, so based on the cost of positive photoresist with the bright field mask and the dark field mask with the negative photoresist, so based on this, the total process varies. And if you are going to just like, let me go from this. If I have a free space, I guess, yeah, I have a free space here. Yeah. So here, let's say you have a space like this, and you need to pattern a triangle out of it. So now if you have to etch everything away, will it be easier, or you need to etch these things away and you need to keep it here? Sorry. So which one will be easier?
The second one would be easier because only inside of the shape would be etched away. But to counter this point, we can make an argument that It depends on what kind of structure we are making. Like
Yeah,
if there's
yeah, 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 yeah.
calculus,
It also depends on that as well. So the main factor is that what kind of a structure we are making, what kind of a patterns we are intended to use, and if there are sharp edges as well. So like this is also an main factor as well. So here there are edges and these things. So if you are trying to make, let's say, circles for resistive random access memories or these kind of things, so like capacitor type of structures and these things, you need a circular one. So based on the structures and everything, it will obviously depend. But let's say on the basic thing, so which one will be like um,
yes.
uh, sorry, there was a network connection. Let me just join in with that. iPad also got disconnected. Yeah, so like my iPad is currently under process of joining the meeting. But yeah, so what I was saying is that just a second, let me just put on my glasses. Yeah, so the main concept was that which one is easier to etch away and which one is easier to create the pattern with. Uh,
Right. To which I asked you, like, it's depend on the structure as well, right?
yeah, so yeah, that just leave it like that. So even if you are trying to, let's say, you are creating a square, let's say that is one of the most easiest one, but it also has corners and those things. But which one is easier to easier to pattern? What do you think?
Easier to pattern.
Yeah.
Right. I think a cylinder would be the cylinder or sphere would be the most easiest to pattern, right?
Yes. Yeah.
Because we won't have to worry about the rounded edges.
Yeah. So in case of squared, what happens is that for the bright field mask, you will have only the center one as the transparent one, and for the photoresist as well. So if you are using a positive photoresist, you will get a direct replica of that pattern onto the substrate itself. Is my voice audible or like is it breaking? Someone is saying that.
No, no, it's audible.
Okay, okay, that's fine. Yeah. So the main concept is that, so why using a bright field and positive photoresist is preferred? So it is preferred due to these kind of a things that there are issues of there can be defects and everything as well. So the issues with this positive photoresist and everything is will not be there, or it will be there, but it will be minimal than the negative one. And similar to that as well. Just a second, what is happening? Is it recording? Yeah. So similar to that, there are several other factors as well. So as there are like cost factors as well. So there are issues like stability issues as well. So with the post so there are two kind of a baking involved in this. So there are pre-baking and post-baking. So based on the post-baking, the stability of your PR is also there. So the positive photoresist are more stable under this post-bake conditions and these things as well. So there are several factors in here, but I'm not sure why my iPad is not connecting. So there are different factors, and based on that, the bright field and the positive photoresist combination is the most used one, and is also the better one as well. Just let me have, I guess, 2 3 minutes. I'm not entirely sure why this one is not joining. Hello everyone. So I'm not sure I'll be able to continue the session today. So the problems were left remaining. So we'll have these problems on the next class, and then after that we'll start with the next class itself. So like you guys can hear me, right? Am I audible?
Yeah, yeah. Okay.
Yeah.
All
Okay.
right.
So
No problem.
Audible,
yes.
sir.
Yeah, yeah. Okay, so then I'll complete the today's problems on the next class, and then after that I'll start the next class itself. Okay. Yeah. Thank you for joining.